Section: Introduction. In this section, we discuss the complexities involved in understanding long videos, which requires more than just recognizing content. We need to reason about time, space, goals, and narratives. For example, predicting the outcome of a football penalty shootout involves analyzing emotional signals and strategies, while finding a hidden ball requires accurate spatial tracking. Similarly, understanding a poker player's decisions involves interpreting deeper strategies, and following a character's journey necessitates plot reasoning. These examples highlight that reasoning is crucial for grasping long videos beyond mere recognition. However, developing long video reasoning capabilities in video language models, VLMs, presents significant challenges. First, creating high-quality datasets for long video reasoning is tough. Unlike fields like math, where structured data is available, annotating long videos with complex elements like time and goals is labor-intensive and subjective, making it slow and costly. Second, using reinforcement learning, RL, for long videos is challenging due to high computational demands and inefficiency. The longer video frames require more memory and processing time, complicating the training process. To address these issues, we introduce LongVILA R1, a framework designed to enhance reasoning in long videos. We have created a high-quality dataset called Long Video Reason, which includes 52,000 question reasoning answer pairs. We use 18,000 samples to kickstart the model's reasoning skills and 33,000 additional samples for reinforcement learning, combining these approaches for better video reasoning. We also established a new benchmark, Long Video Reason Eval, with 1,000 curated long video samples to evaluate performance across 4 areas: temporal, goal and purpose, spatial, and plot and narrative. Our training framework consists of 2 stages, Long-COT SFT and RL for long video reasoning. To tackle the unique challenges of long video RL, we developed a solution called Multimodal Reinforcement Sequence Parallelism, MR SP, which optimizes memory use and speeds up training. Our MR SP system has shown significant improvements, achieving up to 2.1 times faster training on 512-frame videos. LongVILA R1-7B demonstrates strong performance on general video benchmarks and achieves an average accuracy of 67.9% on our Long Video Reason Eval benchmark, outperforming other models. Additionally, we observe that LongVILA R1 improves as the number of input frames increases. In the realm of multimodal reasoning, we note that significant advancements have been made, especially in vision language models, VLMs. Models like GPT-4o and GEMINI 1.5 Pro have pushed the boundaries of visual understanding and context length. While there has been progress in multimodal reasoning, many existing approaches focus on single images or short videos, leaving long video reasoning as a challenging area to explore. Section Summary. In this section, we highlight the complexities of understanding long videos, which require advanced reasoning across temporal, spatial, and narrative dimensions, and discuss the challenges in developing effective long video VLMs due to the difficulty of creating high-quality reasoning datasets and the computational demands of reinforcement learning. We introduce LongVILA R1, a framework that combines a carefully constructed dataset with a 2-stage training approach to enhance reasoning capabilities, achieving superior performance on long video benchmarks. Section: Sequence Parallelism. In this section, we discuss sequence parallelism, which helps us manage long training contexts that can exceed a single device's memory. We have adopted sequence parallelism, SP, as a common solution. For instance, systems like LightSeek and Ring Attention use point-to-point communication, while DeepSpeed Ulysses utilizes all-to-all communication to enhance attention computations. We also integrated Ring-style SP with Ulysses SP. Additionally, LongVILA introduced Multimodal SP, MSP, to allow vision language models to process long context inputs. However, multimodal reinforcement learning presents challenges, as it requires extensive sampling from long, mixed token sequences, especially in complex group optimization tasks. Next, we focus on constructing high-quality annotated datasets for long videos, which are essential for vision language models, VLMs. Current publicly available long video datasets lack quality reasoning annotations. We detail our data construction process, which resulted in 52,000 long video question-answer pairs with reasoning. To curate our dataset, we started with 18,000 long videos from the SHOT 2-story dataset. We then applied a high-quality automated annotation pipeline for chain-of-thought reasoning, resulting in 52,000 question reasoning answer pairs. Each pair is categorized based on the type of reasoning: temporal, goal and purpose, spatial, or plot and narrative. This dataset is designed to support various long video reasoning tasks comprehensively. Given the sensitivity of our model to batch sampling, we adopted a data filtering approach. We used a test scaling method where LongVILA performs inference multiple times on the original datasets. Questions that are consistently answered correctly or incorrectly are labeled as easy or hard, while those with varied predictions are labeled as medium. We use both easy and hard samples for the first stage of supervised fine-tuning, COT-SFT, and medium samples for the second stage of reinforcement learning, RL. This approach ensures diverse predictions, which is crucial for effective learning. The COT-SFT subset consists of 18,000 high-quality reasoning processes formatted in a standard structure, providing ample resources for warm-up training. Meanwhile, the RL subset includes 33,000 challenging long video Q&A, which we utilize in the second stage to enhance reasoning through reinforcement learning. To further improve our model's generalization, we added an additional 110,000 high-quality open-source videos from other datasets. We also introduced an automated annotation pipeline that generates high-quality question reasoning answer pairs from long videos. This process involves segmenting videos into short clips, annotating them with descriptive captions, and using a leading open-source reasoning model to generate diverse question reasoning answer pairs. We designed prompts to encourage the generation of pairs focusing on different reasoning types and included phrases to ensure the model pays attention to visual details. Additionally, we manually curated 1,000 complex reasoning questions across 4 categories to create a new benchmark for evaluating VLMs. Finally, we outline our training pipeline, which consists of 2 stages. 1. Warm-up for long video reasoning using 18,000 high-quality examples for supervised fine-tuning on the MSP system, and 2. Reinforcement learning with dense frames from long videos. We utilize the 52,000 high-quality question reasoning answer pairs to select 18,000 examples for long COT-SFT, equipping the model with essential reasoning abilities and instruction following skills for long video scenarios. We efficiently perform supervised fine-tuning on hundreds of frames using the MSP training system, which significantly enhances the model's foundational reasoning capabilities. Section Summary. In this section, we discuss the implementation of sequence parallelism to manage long context training across devices, highlighting various systems like LightSeq and DeepSpeed Ulysses. We also detail our data construction process for a high-quality dataset of 52K long video question reasoning answer pairs, which supports diverse reasoning tasks and enhances model training through a structured warm-up and reinforcement learning approach. Section: GRPO for long video. In this section, we build upon the progress made by the GRPO algorithm and previous studies on multimodal reasoning training, following the standard GRPO framework to train our model. For each question we pose, our policy model generates a set of candidate responses from the previous policy, along with their associated rewards, which we calculate using rule-based functions focused on format and accuracy. We then optimize our model by maximizing a specific objective function that incorporates the average of the advantages derived from these rewards, while also considering certain hyperparameters. We face significant challenges when applying reinforcement learning, RL, to long videos due to the high computational demands of processing numerous frames. Existing RL frameworks struggle with this long context training. To tackle this, we introduce the Mr. SP framework, which efficiently scales RL for long video reasoning. We utilize a filtered dataset of 33,000 samples for reinforcement learning and add an additional 110,000 samples from Video R1 to enhance our RL approach. This strategy encourages our model to explore and develop more effective reasoning strategies. For long videos, we implement multimodal reinforcement sequence parallelism, Mr. SP, which allows for efficient RL training. This framework uses sequence parallelism during both the rollout and pre-filling stages, reducing overhead and enabling the handling of long videos. In the first stage, we adopt sequence parallelism for video encoding. We divide the input video frames across multiple GPUs, each processing a portion of the video independently. The resulting video embeddings are then combined with text embeddings, allowing us to manage longer videos without overwhelming GPU memory. This parallel encoding ensures efficient use of resources and speeds up processing by reusing the gathered embeddings across multiple rollouts, avoiding the need for repeated encoding. In the second stage, we parallelize the inference process during pre-filling. We reuse the gathered embeddings from the first stage, padding them to a uniform length and distributing them across GPUs. Each GPU computes logits for its assigned token slice in parallel, streamlining the pre-filling process for both the policy and reference models. Our results show that LongVILA R1 to 7B consistently outperforms LongVILA 7B across various benchmarks, with performance differences reflecting the complexity of reasoning tasks. In the VideoMe benchmark, LongVILA R1 to 7B achieves top scores for different video lengths, reaching scores of 60.3 without subtitles and 65.9 with subtitles. Additionally, in our long video reason eval benchmark, LongVILA R1 to 7B achieves an average score of 67.9, surpassing other models like Video R1 to 7B and GPT-4o, and performing comparably to GEMINI 1.5 Pro, especially in the spatial reasoning category where it scores 70.0. Section Summary. In this section, we present the GRPO framework for training our model on long videos, utilizing a multimodal reinforcement learning approach that incorporates sequence parallelism to efficiently process extensive video data. Our results demonstrate that the LongVILA R1 to 7B model outperforms existing models across various benchmarks, achieving leading scores in both general performance and specific reasoning tasks. Section: Scaling video frames. In this section, we discuss how the reasoning ability of LongVILA R1 improves with the number of input video frames. Our results show that with just 16 frames, LongVILA R1 to 1.5B performs similarly to LONGVILA 1.5B. However, as we increase the frames to 512, LongVILA R1 to 1.5B consistently outperforms LONGVILA 1.5B, achieving a score of 64.3. We observe that LongVILA R1 to 1.5B shows steady improvements as we scale up, while LONGVILA 1.5B struggles with 256 frames and performs worse with 512 frames due to its limitations in processing dense visual data. This indicates that LongVILA R1 to 1.5B is better at integrating and inferring information from longer videos. Next, we examine the effectiveness of our training stages and datasets using LONGVILA 1.5B as a reference point. Our evaluations on the long video reason eval show that skipping certain training stages leads to lower accuracy, while training with our COT-SFT dataset yields better results than other datasets. Additionally, adding reinforcement learning after the warm-up phase enhances performance compared to using only supervised fine-tuning. We find that skipping COT-SFT and training directly with reinforcement learning results in a drop in accuracy. Using Video R1 datasets in both COT-SFT and reinforcement learning stages also leads to poorer performance compared to our datasets. Finally, we analyze the training efficiency of our Mr. SP system using one A100 node with 8 GPUs. We measure the time taken for each training step after warming up and average the results to reduce variance. Using the LONGVILA7BR1 model with a batch size of 1 per GPU and a rollout number of 5, we compare the runtime across different frame counts. Our findings reveal that the baseline runtime increases sharply with more frames. However, using only stage 1 of Mr. SP significantly boosts efficiency up to 512 frames, although we encounter GPU memory issues beyond that. In contrast, the full Mr. SP system consistently reduces runtime, achieving up to a 2.1 times speedup at 512 frames and efficiently scaling to 1024 frames, demonstrating the advantages of combining sequence reuse and parallelism for long video reinforcement learning training.